thank you for the invitation to speak in this workshop, and thank you for the introduction. So let H be a Hilbert space, as we saw on Monday. This is just a slide of notation, right? So I'm going to write blackboard bold MN for complex matrices, because I don't want to write C for the complex numbers everywhere. It takes too much space. Okay, and as often is the case in operator algebras and random matrices, I use lowercase trace to denote the normalized trace, and uppercase trace to denote the unnormalized trace. And the norm and inner product with respect to the normalized trace are there as written there. The inner products will be linear in the second coordinate. As someone once observed, inner products can either be linear in the right coordinate or they can be linear in the wrong coordinate. So going to do the right one. Okay, yeah, and you have this space of self-adjoint matrices. And importantly, because Lebesgue measure will come up, the way that I want to understand Lebesgue measure on matrices is I have an inner product, I choose an orthonormal basis and then transform it, okay? But it's not the same as just looking at the entries of the matrix, because I used a normalized trace. Well, that's just a warning. So the main motivation for today is to study matrix models. And you're studying random matrices here. So this is going to be just a classical density, but on the space of matrices. And the way we define the density is by using some kind of matrix function, right? Where you apply a function by functional calculus. And later on, we'll see in multiple variables, we'll use non-commutative polynomials for this. Right? So basically, the study is of classical measures, but those that are defined by a special class of functions, right? Somehow invariant functions or the correct class of functions which are just based on matrix operations. And so if you start off in the one variable case, this is by now a well-established theory, but you can look at this density like this, and you can also think about this in terms of the potential here in the exponent. You can think of this in terms of eigenvalues as well. You're taking a sum over f applied to each eigenvalue with a certain normalization depending on n. All right, so this should be very reminiscent of classical things in statistical mechanics, where you use some potential and then you try to look at Gibbs states for that potential and then see what happens as n goes to infinity. In fact, people have studied just this behavior, just the behavior of this thing, just based on the joint distribution of eigenvalues, and this is very close to models of Coulomb gases and other things like this. So I'm going to study a random self-adjoint matrix with such a density. The density, as I've written above, will be invariant under unitary conjugation because the functional calculus is and the traces. And the first thing you care about for a single matrix case is the empirical spectral distribution, which will be a measure that depends on the matrix that has point masses at each of the eigenvalues. Right? And so this measure is still random. So there's this classical theory, which you can see in the paper cited there, that what happens when you analyze the density for this, you look at some kind of density in terms of the eigenvalues, and then you have some kind of term which measures the repulsion of the eigenvalues. And this comes from basically disintegrating the measure with respect to the eigenvalues and with respect to the unitary conjugation. And so you end up with some formula that to define the large n limit of this, depending on this potential function f you put in, you want a measure that maximizes this logarithmic energy minus the integral of this function. And if you have such a unique maximizer, then this will be the limit of the empirical spectral distribution almost surely. And
what is 8? Just to know history.
Let's see. I think it's called. It has 3 authors. It has it's about I think the statistical mechanical approach in random matrix theory. Boutet de Monvel and Scherbina and someone I forgot. But okay, that's why I didn't say it, because I didn't remember. Anyway, and to be even more classical, right? If you just take your potential to be quadratic, then the measure you get is the Wigner semicircle law, right? And this was, and Wigner is studying this because he thought that this was a toy model for energy levels of atoms. Okay, And so this gives you a kind of a theory that's completely in line with statistical mechanics, as well as our study of entropy and information geometry that you're all familiar with, hopefully. That this is a version of a Gibbs law, and that the role of entropy is played by this logarithmic energy. And you can actually show that if you take the differential entropy of this density on the matrix algebra, and you include appropriate normalizations, then the large N limit of this will be given by this logarithmic energy. And so this motivated Voiculescu's study of free entropy, right, which in the one variable case is this logarithmic energy. But what I'm going to talk about today is going beyond the single matrix case, where things get a lot weirder and a lot more difficult to understand. And so we're going to be studying, say, if you have a non-self-adjoint matrix, right, which if you wanted, you could write it as a self-adjoint plus I times the self-adjoint. So that's like studying two self-adjoints that don't necessarily commute with each other. And then more generally, studying just several matrices together. So first I want to motivate, like, what are the functions that we're using here, right? Like I said, we're trying to look at classical probability densities, but restricted to a certain class of functions that we think are kind of the right invariant functions and that we want to describe in a large N limit. So one fact that I'll recall, which was proved for a single non-self-adjoint matrix by Specht many years ago, and I don't have the citation for that, and then only finally recently was actually written down properly for the several matrix case, that in order to test if you have two tuples of matrices, in order to test if they're unitarily conjugate to each other, then all you need to do is test all possible star polynomials evaluated on both matrices and make sure that they're the same. And there's a kind of dual statement to this, which is so maybe if the first statement is telling you something about, okay, when do the two matrices have the same distribution with respect to the trace, the second statement is talking about the functions. Right? So if you have, for instance, a polynomial function, meaning a polynomial function of the real and imaginary parts of the entries of a matrix, and if this function happens to be invariant under simultaneous unitary conjugation, then it is a so-called trace polynomial. It's some function that's obtained from the traces of non-commutative polynomials by adding and multiplying them together. So here's some notation on the non-commutative polynomials. Yeah, so they're non-commutative, so if you have a monomial, then it matters which order they're written in, right? And so this is just an algebraic object, and as a vector space, it has this basis written here. Then I want to consider star polynomials, because then I want to have polynomials in the original variables and their adjoints, so I introduce this formal star algebra. Then you have the algebra of trace polynomials. So you take things from the star polynomial algebra, you take traces of them, and then you take sums and products of these traces. And you build this first as a formal algebraic space. And each of these spaces defines objects, they're objects which can be evaluated on particular matrices, right? So you can plug in particular matrices into the polynomials, and then this, of course, you evaluate each of these formal trace symbols as the actual normalized trace on matrices. So then you can start out studying multi-matrix models where you have this function v, which is some trace polynomial, or a similar function. You may want to consider trace polynomials in resolvents, for instance, because these things have a nice, they're nicely bounded at infinity, and they have, and the derivatives are bounded. But basically some kind of functions like this, and you have this measure on tuples of n by n matrices like this, and then you want to have an analogous result as you have in the single variable case. So you might want to ask, well, if I take trace polynomials f, and then I want to know if the random quantity f of xn will converge as n goes to infinity, and what kind of object describes the limit. And then you want to go further and to understand, well, how does the entropy of this behave in a large N limit, and how does the Wasserstein distance behave in a large N limit, and how do these things relate to each other? So in order to describe the object, we have to think a little bit more carefully, because you can't just say, oh, I just look at the eigenvalues, right? Because now you have several matrices that don't commute with each other. And even if you had a non-normal matrix, the eigenvalues are not complete information about how it behaves. Right? So what we're going to look at is these non-commutative moments, right? Because if you had in the single variable case, you could just think about the moments of the empirical spectral distribution, which should be the trace of some functions of x. And so now we're just going to consider this in traces of some functions, but just non-commutative polynomials. So the object that we have is not going to be a classical measure, but it's going to be, instead of a functional on classical functions, it will be a function on non-commutative polynomials. So you take this star algebra of star polynomials, and you consider linear functionals which have the right normalization properties, right? So you want that the law applied to 1 is 1, and you want that it's positive, right? Which would mean that mu of p star p is greater than or equal to 0. And the third property is traciality, right? Which is what you would expect if you're applying the trace to some polynomials in matrices. Yeah, you'd expect it to have this property. And the last property is an estimate of how it grows with R, which I think should have a left absolute value sign as well. And this is just what you would expect to happen if you're plugging in things with operator norm bounded by R, because then if you take a product of them, it's bounded by R to the L, and then if you take the normalized trace, that's bounded by the operator norm. And this is, yes?
In this star polynomials, how do you multiply? Because you have to preserve also this property.
You just there's no difficulty in multiplying.
Just multiplying, but then the star of it is not.
Yeah, so the star, the star of PQ is Q star times P star, as you would expect from, how it behaves on operators.
Okay. Because they're each, so it's not, okay.
Yeah. Yeah, all right, so anyway, we view this as an analog of probability measures, and here, since I have this bound, this is an analog of probability measures that's supported on the product of R disks, right? Where each variable is bounded by R.
By the way, what is if you replace the R to the L to the L to the L in front? Make that a little bit larger, does it still work?
I mean, there's various enlargements you can take. I mean, ultimately, you probably want to consider affiliated operators in the tracial von Neumann algebra rather than going like halfway to some other weird intermediate thing.
With L to the L, I think that still works. You can make that. You have to just, there's this Hamburger moment problem where you have to be a little careful.
Yeah.
Okay.
Yeah, I think though there are enough subtleties and difficult things that happen even if you assume that they're bounded. I don't need to try to worry about this yet. Okay, so then what is the analog of probability spaces? You've probably seen such things in previous talks here. So I'm going to consider tracial von Neumann algebras. So it's a pair of a von Neumann algebra and a faithful normal tracial state, right? So von Neumann algebra, it's a star subalgebra B of H, closed and weak operator topology. Hey, and the tracial state has similar properties as the trace on matrices and also similar properties as the laws that I wrote down before. Namely, it's unital, it satisfies this tracial identity, right? It's positive, and then here is the faithfulness. And so you want to think of this M as an algebra of random variables, right? So just like in the classical case, you can have a probability space, you can form the L infinity space, right? And this is an algebra of bounded random variables, and the functional you consider on this is the integral or the expectation. And similarly, the matrix algebra is an example, right? You have a matrix algebra and you have the trace. It satisfies all these properties. Okay, so then how do these two things relate, right? We have these abstract non-commutative laws, which is some kind of functionals on polynomials, and then you have these concrete objects, which are the von Neumann algebras. Well, I don't know if a von Neumann algebra is concrete, but yeah, it's not an algebraic object. So for each tuple of variables in a von Neumann algebra, and if the operator norms are bounded by R, then there's an associated non-commutative law, and the law of it is the thing you apply to a polynomial by just evaluating that polynomial on X and taking the trace in the von Neumann algebra. And it turns out that every non-commutative law actually arises in this way, and this is basically the GNS construction, but maybe is a little bit of more work because the polynomial algebra isn't a C-star algebra, so you have to think a little bit. But every non-commutative law arises in this way, and there's also a natural weak star topology, which is given by point-wise convergence, mean convergence of each moment. Right, and here again, also, if you remove the bound on the operator norm, then maybe you want to think carefully about what topology you want. Right? But if it's bounded, there's a clear answer for the weak star topology. So besides this, as this is what Dima talked about on Monday, there's a Wasserstein distance in the non-commutative setting. And the way we think of this is maybe from a probabilist viewpoint, right? That what is a coupling? A coupling of two measures mu and nu is you build some probability space and you build two random variables in there which have those distributions mu and nu respectively. And then if you want to study L2 Wasserstein distance or other types of Wasserstein distance, you try to vary the probability space and put these x and y there in different ways to make the distance as small as possible in L2. Right. So this is exactly how this free Wasserstein distance is defined. And there are some things that behave the way you would expect, like if the x and y actually generate commutative von Neumann algebras, the distance is the same as you get in the classical case. But there's a lot of weird things that happen as well. So firstly, it's not separable. This space of non-commutative laws is not separable with respect to the L2 Wasserstein distance, right? And so that might be kind of bad. Secondly, another reason, and this maybe follows from the first point, right? Because it's compact with the weak star topology, and so if it gave you the weak star topology, then it would have to be separable, right? But it's not. And so we see, in fact, that the Wasserstein distance gives you a strictly stronger topology on this space of laws than the weak star topology. And again, this is assuming that they're bounded, right? In the classical case, the only thing that can go wrong is sort of the behavior at infinity. In the non-commutative case, you assume that they're bounded and the topologies are still wildly different. And then, due to the MIP star equals RE paper, you have the following very weird fact that the non-commutative laws that arise from finite dimensional algebras are not dense. Okay, so if you think classically, of course, you can approximate measures by combinations of point masses, right? So you can approximate measures with finite support. The analogous statement in the non-commutative case, based on the MIP star equals RE, you cannot do this. And furthermore, if you think about suppose now that you just consider laws coming from finite dimensional algebras, and then you want to consider the weak star closure of them, right? And these are the so-called ones that live in so-called con-embeddable von Neumann algebras, right? But you could also consider the Wasserstein closure of these laws that come from finite dimensional algebras, and what you get from that is all the ones that live in amenable von Neumann algebras. And if you know about von Neumann algebras, like most of them are not amenable. Like free group von Neumann algebra is definitely not amenable. If you're in quantum information, maybe it isn't that bad because, in a sense, you often study infinite tensor product of finite dimensional things, and that would be amenable von Neumann algebra, right? But in terms of von Neumann algebras in general, this is very restricted, right? So you have a lot more things that can be approximated in weak star topology than you can in Wasserstein distance. And in fact, when you study this random matrix theory and you study these multivariable matrix models, and you say that as n goes to infinity, the non-commutative law of them converges to something, you can only get it to converge in weak star topology. Most of the time, you cannot get it to converge in Wasserstein distance because you get non-amenable von Neumann algebras. So, because of all of these properties, I feel like if we're building this zoo of non-commutative Wasserstein distances, in a sense, we're not really dealing with like mammals and fish and birds, and we're basically dealing with dragons the whole time. Okay, so after we define this Wasserstein distance in the non-commutative setting, we then have what the analog of entropy is. So there are actually several types of entropy, which we don't know whether they all give you the same answer, right? So Voiculescu came up with several different definitions. So we have a zoo of choices of entropy as well. And I'm going to focus on the one which is more closely related to the matrix models, which is this so-called chi. And I'm not going to write the technical definition, but I'll tell you one way that you can describe it, which is maybe intuitive for this setting, that if you consider some random matrix models, and if the laws of them are converging in the weak star topology to a certain non-commutative law mu, and if you have some kind of reasonable bound on the probability of a large operator norm, which don't worry about what it is specifically, then the entropy of the classical matrix models with a certain multiplicative and additive normalizations is at most the chi. And actually you achieve equality for some sequence of random matrix models. And don't worry about the normalizations either. I mean, you can just think about if you know what the entropy is of the Gaussian case, and then based on computing that, you know what the normalizations should be. And a more interesting fact is that we don't actually know whether taking lim sup and lim inf give you the same answer. All right, so we don't know whether the limit as n goes to infinity exists. Okay, we have a question from Zoom.
What is h? I forgot, sorry.
So, I think he asked what was h. Is that true?
H?
Did you ask what h is?
So h, I just mean the classical differential entropy. So this would be the integral of minus rho log rho, where rho is the density, right? Because this is on a classical, space of matrices, which is the finite dimensional space.
Okay, thanks.
Okay, so returning again to the multi-matrix models, we have some results that are similar to what you have in the single matrix model, but there's a lot of stuff we don't know as well. So for instance, and it's not hard to show this, right, that if there's a unique law maximizing this entropy, and if the lim sup is actually a limit, then you get that these laws are converging almost surely. And a lot of the main results happen in the case where you have some V which is strongly convex, and in this case you can show the convergence of this. And the way that you show the convergence is actually similar to some techniques that were mentioned already, that you have this method of sampling the Gibbs distribution by starting in some initial measure and then flowing along some SDE, right? So this Langevin equation. And this is one of the few things that we can control in a dimension independent way. Right, so you have to understand how this evolves, and then you have to understand how the large n behavior of the Brownian motion behaves. Right? And so we have this description through free semicircular Brownian motion, which will come up in more detail in the later talks. Right, so those are the sort of tools that you often use to show this convergence. And then furthermore, it's also true that because of this V being a nice function, that if you get this particular model to converge in non-commutative law almost surely, then you also get that the large n behavior of the entropy is exactly this free entropy that you want. And then as far as the convergence of the Wasserstein distance, is a lot less that we know about this. So we know that we have the Wasserstein distances of the random matrix models converge to the free Wasserstein distance in certain scenarios, namely if you have one of the potentials to be quadratic and the other one to be one of these convex potentials. And the work of Guillen and Shliak-Tenko in 2014 constructed these optimal transport maps, and we knew that they were a gradient of a convex function. But at that point, there wasn't the machinery of optimal transport theory developed to say that that was enough to imply that this is optimal. And the reason is because since in your Wasserstein distance, you allow arbitrary von Neumann algebras, there's no guarantee that there's not some other weird von Neumann algebra, like something that's not Kahn-embeddable, that you cannot find some better coupling in there that does better than the one that you have with your function. So you need to be able to rule that out somehow. And it's not well understood what happens in the cases where these potentials are not convex. And in fact, if you examine the MIP star equals RE result, this also gives you some kind of obstruction, because you can actually show using some kind of just like elementary duality arguments that if you have non-commutative laws that cannot be approximated by the ones in finite dimensions, it will happen that sometimes you'll have some tuples of matrices, some laws that come from finite dimensional things, and in order to have an optimal coupling of them, you need to use something that does not have finite dimensional approximations. So there's no control, you cannot control what kind of thing you need to use for the coupling just from some kind of assumptions on the inputs. And so this is kind of bad, but in a sense, this might seem like a a stupid counterexample to this, because you could just modify the distance to only consider the couplings that occur in the con-embeddable von Neumann algebras, and then ask the same question. Okay, so coming at the topic of Wasserstein geometry, information geometry, it's natural to try to do something of the following form. Say you want to prove some facts about the entropy and Wasserstein distance for non-commutative laws. So take, for example, the displacement concavity. I say concavity because of the choice of sign conventions, but you want to know that the entropy is a concave function as you move along a geodesic in the Wasserstein space. Right? So this was, McCann showed such concavity or convexity for many different kinds of functionals in the classical case, and in particular for entropy. And so how could you do that? Well, if you try to do it by means of matrix approximations, you want to find some matrix approximations for the two laws. So we have some random matrix models, xn and yn, that converge to them. And then you want the Wasserstein distances to converge. And then you also want the entropies to converge with the appropriate normalizations. And if you can do those things, then basically you can apply the classical results to the random matrix models and then be done. And so this sounds like a great plan, like what could possibly go wrong, but definitely a lot of things can go wrong. So here's what things could go wrong. Firstly, this conjecture is just not true, and in fact, things go wrong even if you only care about having the correct entropy on one of them, and you don't care about the entropy on the other one. So what goes wrong? And maybe I'm not going to exactly explain the counterexample to this, but maybe I'll explain the counterexample this is derived from. And the problem is that the matrix models that you have with this potential V do not behave well under taking marginals. You can take marginal of it, and the marginal will not be a matrix model of the same form with a trace polynomial potential, even approximately. And in fact, and the claim of having matrix models that achieve the correct entropy does not work well under marginals, which is what I'll write down here. So you can consider some kind of non-commutative law of x1 and x2. And again, these are not self-adjoint. So in a sense, each one contains two self-adjoint things. And you can take x1 to be the free analog of Gaussian, right? So this is the nicest possible thing. And take the x2 to be, it doesn't really matter what x2 is that much. You just want it to almost commute with x1, and you want it to be non-trivial. So to be non-trivial, for instance, I could imagine that its L2 norm is bounded below, and its trace is 0. And I'll assume the operator norm is bounded above, or whatever. Right, so now let's suppose that I have some random matrix model whose non-commutative law is converging to the law of this x in probability. Right? And then I'm going to claim that the entropy that you get when you just look at the marginal from x1 can never achieve the value that we want. Right? And why does this happen? So there's actually several ways to see this, and the proof that I wrote here is not what I wrote in the paper. What I wrote in the paper, I wrote something, just with some conditioning and conditionally linear changes of variables that sort of, from general properties of entropy, this somehow cannot work, right? But I'll tell you what was the motivation for this example. So let's consider the following formula here. Okay, so this is a formula that for some A, then this is saying if the infimum is small, then there exists some B where it almost commutes with A, and the trace of B is small, and the 2 norm of B is close to being 1/2, at least 1/2. No, so those are exactly the conditions I wrote in the previous slide, right? And this is just the formula that captures if you're some B that satisfies this, then it's satisfying this property. And so if you have the random matrix models for x1 and x2, right, because they're converging, they're going to be satisfying such a property with high probability. So the x1 in particular is going to satisfy that phi of x1 is smaller than epsilon with high probability. But now we run into a problem in that the set of A which satisfies this actually has very small volume as epsilon goes to 0. And so therefore you cannot have high entropy, right? Because if you support it on a certain set, the largest entropy you can have is the entropy of uniform distribution on that set. So if the volume of the set is small, that constrains how much entropy you can have. And how can you estimate the volume? Well, let's just consider, instead of taking the B, you could massage it a little bit and take some projection that's in a star algebra generated by B, or von Neumann algebra at least. And I guess I'm assuming, okay, so maybe this is just true approximately or something, right? But you can get some projection out of it. Right? If B was self-adjoint, you'd take just some spectral projection of it. And then you'll have that so A almost commutes with some projection. And you can view the projection as giving a way to decompose the matrix in a block diagonal form, where you have one block corresponding to P and the other block corresponding to 1 minus P. So if you almost commute with a projection, then that means it's close to being block diagonal. And if you consider what's the dimension of the space of block diagonal matrices relative to the whole dimension, right? It's a smaller dimension by a certain fraction that's independent of n. Right, so it'll be like the dimension will be like trace of p squared times trace of 1 minus p, or trace of p squared plus trace of 1 minus p squared times the ambient dimension. It will be smaller than 1. And so in particular, the volume will have to be very small because you'll be in an epsilon neighborhood of this lower dimensional set. Right, so this whole argument, this was used by von Neumann to study the problem of almost commuting matrices that aren't close to something that actually commutes. And it was used by Voiculescu in order to study various properties of von Neumann algebras using free entropy. Right, so this is a well-known phenomenon. But so the problem is, if you just look at the marginal, if you just look at the non-commutative law of x1, the x1 doesn't remember any information about x2. Right? It doesn't remember that there exists something that commutes with it. But if you have the matrix model and you take the marginal, then it does have some kind of residual memory of the fact that there exists something that commutes with it. And so it forces it to be supported on the smaller dimensional set, and so it cannot have enough entropy. All right. So as we see from this, defeating the dragon is difficult, but you have to try. This was something that was written in the first Polish language encyclopedia, of course written in Polish, even though the captions were in Latin. But we're going to try to figure out what goes wrong here, and is there any way to fix this, and can we actually understand what makes it difficult? So one of the important things we need to do is to have Monge-Kantorovich duality, or we want to have, so this is written for the L2 setting, right? So what you want is an analog of this theorem that if you have a L2 optimal coupling, you can test this by certain pairs of convex functions, right? So you have two convex functions, phi and psi, such that it's going to be the phi plus psi will be always greater than or equal to the inner product of x and y. And when you have an optimal coupling, then the expectation of phi of x and the expectation of psi of y will equal to the expectation of the inner product of x and y. And if you control the expectation of the inner product, then it also tells you you can also control the L2 norm based on this, because you can just expand the L2 norm of x minus y squared. Right, so this is a classical result, and by the way, the gradient of phi gives the transport function from x to y, and the gradient of psi gives the transport function from y to x. And the phi and psi are related to each other in a certain way that this psi will be Legendre transform of phi. So you have this formula with soup. So now, if we're trying to imitate this in a non-commutative setting, we want to have at least the Legendre transform to work well, right? And this is all, and this idea is actually how we showed that the optimal couplings from Guillenet and Sliatenko were actually optimal by studying Legendre transform. Okay, so we have this real valued trace polynomial function, and then you want to define some Legendre transform of this, and then you hope that the Legendre transform of this is also a nice function which you can understand. And of course, if the phi is uniformly convex or strongly convex, then this does work because you can solve for where the minimizer is by just a first derivative test. But it doesn't really work well in general, because it happens that Well, firstly, you can see that this isn't going to work because this Cm, right, you're taking the supremum over m. And it turns out that if you change what m is, if you like embed into a larger m, you can get a different value for the supremum. And I mean, and you know this exactly because of the fact that if you change the ambient algebra for m, then you can get different answers for the free Wasserstein distance, right? So this is sort of, I guess this is true for similar reasons. Maybe because this is true in, at least, yeah, if you apply this argument to finite dimensional matrix algebras. And so then this thing is something which depends on more information than just the non-commutative law of y. And so in particular, it cannot be approximated by a trace polynomial because trace polynomial only depends on the law of y. Right, and furthermore, I wanted to consider this a paradox, right? Because in finite dimensions, if you fix the dimension n, then you know that any function which is unitarily invariant can be approximated by trace polynomials. Yeah, because if you have and so in particular, you take this Legendre transform, it's a function that's invariant under simultaneous unitary conjugation, and well, you could approximate any function, any continuous function in finite dimensions, you could approximate it by polynomials. Then you could take your polynomial and you could, and it might not be invariant, but you can average it and get a polynomial that's invariant. And then by Processi's result, this is trace polynomial. So this function, if you fix n and you look at this on n by n matrices, it can be approximated by trace polynomials. But this cannot be done in a uniform way based on n, because of what I said before, that it's not possible to do this in most von Neumann algebras. So you can do it for a fixed n, but as n goes to infinity, it becomes harder and harder to approximate it. Right? And so there's actually a sort of deep reason for what goes on here, which you can think about in terms of model theory. Right? And maybe none of you know what model theory is, but the idea here is simple. You want to consider that this thing, you have some kind of formula, which might be a trace polynomial, and then you apply an operation like supremum. And supremum is basically a quantifier. And so then you get out this new formula here. And if some object is said to have quantifier elimination if you can approximate the formula with the sup by some other formula that doesn't have any quantifiers. Right? And this theorem from Ilias-Farah says exactly if you have like infinite dimensional, non-trivial tracial von Neumann algebras, say those which are simple, then it can't have quantifier elimination. So there's always some formulas that you can take with some supremum that you cannot approximate with formulas that have no quantifiers.
You have to use continuous logic, right, in order to...
Yeah, this is continuous logic. And I'll write some more about this in a moment. And by the way, just to underscore that this is something non-trivial, if you take classical probability space, then it does have quantifier elimination. And basically, this is like the statement that if you have some formula that depends on certain random variables, and then you want to take a sup over some other random variable, you can figure out what the sup is just by acting pointwise on each point of the probability space. So you can just find the pointwise supremum of the thing you're trying to evaluate. And so then you can express it in terms of something that doesn't quantify over random variables. But this is fundamentally different than the classical case. And by the way, if you wanted to say, well, what if I only wanted to use one quantifier, but not two? Then this is all. You can also not do this. You cannot take formula with two quantifiers that are alternating inf and then sup. You cannot approximate it with one quantifier. Okay, so what do I mean by these formulas? So firstly, if we're considering the goal of having some nice class of functions that includes trace polynomials, and you want it to be a vector space, and you want it to be closed under these partial suprema and infima, you're sort of forced to allow iterated suprema and infima, right? Because there's no way that you can just reduce it to only one quantifier or zero quantifiers. But these things that you get from these iterated quantifiers are some sort of logical formula in an at least analogous to logical formulas, where you don't take true false values, but you take real values. And so then your connectives are not like and or, but they're kind of continuous functions, and the quantifiers are not for all and there exists, but they're supremum and infimum. So there's this whole theory of continuous logic. And so here's one example what a formula would be like. You might have some alternation between sup and inf quantifiers and then something that you apply at the end. And it turns out that formulas like this, where you put all the quantifiers outside of everything else, are dense. So it's you don't need to think necessarily about the general formulas. Okay, and maybe this seems like wild and out there to think about model theory, but if you just think about two quantifiers, right, doing a sup and then an inf, this is just a saddle point problem, right? So this thing comes up naturally in analysis, and maybe you don't think about like three nested sups and infs in general, but you know, in a sense, once you have two, then maybe you're not that far from looking at this general mess. So when you have these formulas, then just like the trace polynomials, there's an evaluation of formulas. The evaluation of formulas works by just plugging in certain elements from a von Neumann algebra, using the trace from that von Neumann algebra, and then the suprema and infima are then evaluated over the unit ball. There's a completion of the space of formulas, which is called definable predicates, which I don't know why, maybe the name is completely different, but think about, you know, the predicate is something that takes some logical value, which we're using real numbers for instead of true false, and being definable means that somehow you can approximate it by these formulas. All right, and then you have the analog of the probability distribution, and this becomes the type. So the type, instead of using, you know, classical functions or using non-commutative polynomials, now you use these formulas with suprema and infima, and you can define the type of x, and it's just a mapping from the vector space of formulas into real numbers. And so then you have this space of types, and then it also has a weak star topology, right? And so as you're studying this and thinking about, well, what if we take these iterated suprema and infima, you run into certain issues, which is, firstly, just consider the case if the thing didn't depend on x at all, but you just took iterated suprema and infima and then got out, in the end, a number. Right? And so this is what you call a sentence. And if you take this, and you take this, these over the unit ball of n by n matrices, we do not know if the limit as n goes to infinity of this evaluation on n by n matrices exists. And I think that's kind of bad, right? Because if we're trying to develop like the asymptotic theory of what happens as n goes to infinity, you need the limits of these basic things to exist. In fact, it may be true that the limit doesn't exist. And the reason is because there's been recent work of Alexeyev and Tom on the analogous questions for where you look at like behavior of permutation groups with Hamming distance as n goes to infinity instead of matrix algebras. And then because you can recover the diagonal matrices as somehow or you can recover the permutation group from looking at the normalizer of the diagonal matrices, and then you can kind of deduce from this that if you looked at such iterated suprema and infima, and if you allowed some of the suprema and infima to be over unit ball of matrices and some to be over diagonal matrices, then the limit does not exist as n goes to infinity. So if you do, you know, some kind of just like saddle point problem and you do it over matrices with these nice functions, then you get some very wild behavior, perhaps. Another thing that's kind of bad is that you cannot compute things. And this is a consequence of MIP star equals RE. And this was written by Goldring and Hart that say there's no algorithm that if you're given a real value trace polynomial with just coefficients and rationals, because you want to make this kind of a discrete thing to talk about computability, there's no algorithm that will output you a rational number that describes what is the infimum of this thing over operator norm ball of matrices in the large n limit. So you cannot actually, I mean, there's algorithms that would give you some lower bounds, or at least one direction, but you cannot actually have an algorithm that reliably tells you you're within a specified distance of this limit. No, so I think based on this, I would say that matrix algebras really are amazing creatures, and you can learn about all there is to know about their ways in a month, yet after 100 years, they still surprise you. All right, so despite the fact that there's a lot of bad things that happen, there are some very good things that happen with this space of types. So I guess I have not that much time, so I'll try to go quickly. The first nice fact is that if you look at this, the Wasserstein distance on this type space, then there's a sense in which this corresponds to the distance between automorphism orbits of tuples into von Neumann algebra. So given any von Neumann algebra, tracial von Neumann algebra, you can embed it in a larger one in a natural way, in a way that preserves the values of formulas, the so-called elementary embedding. And in this larger one, everything with the same type is conjugate by an automorphism. And therefore, the Wasserstein distance gives you the distance between automorphisms. And I think maybe this is perhaps natural in a non-commutative setting as well, that you might, you have, different kinds of couplings. You have unital completely positive trace-preserving maps. You have factorizable maps, and you have convex hull of automorphisms. And the automorphisms in the finite dimensional case are unitary conjugation. But in the infinite dimensional case, automorphisms are not unitary conjugation. But you have some kind of coherent theory for what is the Wasserstein space that you would associate to automorphisms. So another good thing is that you can obtain an analog of Monge-Kantorovich duality. You just look at these so-called definable predicates that are convex, and you have basically the same statement as you would want. So if you have two types, then you can find convex definable predicates where they satisfy this inequality as analogous to the classical case, and that equality is achieved when you have an optimal coupling of these mu and nu. Okay, maybe I'll skip the remarks on this, but maybe Wilfred may mention more about this. And then I also adapted the notion of free entropy for types for the entropy chi. I mean, the proposition that I wrote before, that it's the supremum of limits of classical entropy of matrix models, was still true, but you don't necessarily want to take limit as n goes to infinity, but you just restrict to limits along an ultrafilter, which is like some kind of subsequential limit. And it turns out that you can at least get part of the way to having a good way to combine matrix models that have the right entropy and Wasserstein distance in this setting. So you can't necessarily say, we don't know yet if this entropy will be concave along the geodesic, but at least we can get some kind of lower bound. But it's one-sided. It's a lower bound in terms of the left endpoint and a lower bound in terms of the right endpoint. And the reason it works is because the conjecture, the naive conjecture that I wrote before, does actually work in the one-sided form in this case, that you can find matrices, matrix models where the types converge in probability to the specified types, the Wasserstein distances converge, and the entropy of one of them converges. And it's a key point in doing this, right? The reason you can do this is because you have a Monge-Kantorovich duality with some nice functions, with functions that have the weak star continuity property on the type space that you want. And because you have these nice functions, phi and psi, you can use those functions to build random matrix models. You can build some potential out of these functions, use that to define a matrix model, and then play with that, right? But if you have functions, but in order to do this, you need the weak star continuity, because for the matrix approximations, you can only get weak star convergence. So you need to build matrix models, you basically need to use some kind of...
Before you go away from that, so you can construct these matrix models for one side, but you cannot approximate the convex combinations, right?
Yeah, so the way it works is...
T, right, in every T, right?
I start out with a given matrix model for one of the sides, and then I extend it to a matrix model for the other side.
Right,
and
but
then,
before you cannot do it somehow with all parameters in T, or is that not clear? If you have the page before, you probably wanted to do this for all T's automatically, for these convex combinations you looked at.
Well, so in order to prove, because you have a supremum over possible limits of classical entropy, you need to be able to arrange the left side and the right side to be whatever you want, right? So of course, it is possible to say that there exists random matrix model for each given point, but you need to have it for the whole path, and you need to be able to control both the left and the right endpoints. And I can control one of the endpoints, just put in whatever I want for one of the endpoints, and then extend it to something on the whole thing. Right? But in order to do this, really, I mean, you need to be able to arrange that both of the endpoints have large enough entropy. And in order to do this, basically, you need to understand the entropy itself and to kind of phrase it as some kind of optimization problem. And this is what Wilfred and Aaron will mention a bit more. Okay, so this is a classic formula, maybe in a sense, in this case. So the Bouet and Dupuy gives a version where you look at different, multiple times in the Brownian motion. But basically, if you're taking, some kind of heat flow or expectation with respect to Gaussian of some exponential of some functional, then if you take the log of this, then this amounts to stochastic optimization problem, right? Which would correspond to some Hamilton-Jacobi equation. So this is basically like Hopf-Kohl transformation, and then viewing the thing in the logarithm as this optimization problem. You write this out for the matrix setting, and then in the matrix setting, you can understand, well, what's the large N behavior of the Brownian motion? We use the free semicircular Brownian motion to understand that. And so there's some kind of optimization problems you can set up. And just like the other optimization problems that I mentioned, there's an issue of like which algebra you use to do the optimization and which filtration you use and all that. So you have to think about that. But ultimately, if you can resolve these issues, then you should be able to express the entropy using something like this. So I think I won't say any more there, but you stay tuned for Wilfred and Aaron's talks where we study exactly these stochastic optimization problems in the free probability setting. And also there will be more future works related to these talks.